Hello friends, this is Dr. Hemant Chandak, and today this video lecture is dedicated for the reactions of the benzene, which will cover the curriculum of the semester 1 of BSc of SGB Amravati University Amravati. The learning objectives of this particular video lecture would be to understand the reactivity of benzene, to know the general nature of aromatic electrophilic substitution, which is the most common reaction in the uh, the all benzoate system. Thereafter, we will see the mechanism of few common aromatic electrophilic substitution reaction like nitration, Friedal Craft, alkylation, Friedal Craft, acylation, and nuclear halogenation. The mechanism of side chain halogenation and the Birch reduction will be covered in the next lecture in the series. Moving forward, let us try to understand the nature of the benzene. Now we all know the molecular orbital picture of the benzene, and you know that benzene is a sandwich structure where you have the lobes of the p orbital which are overlapping laterally above the sigma plane and below the sigma plane, resulting in the formation of a sandwich structure. So and it satisfies the Huckel's aromatic rule of 4n plus 2 pi electron system. So this system, benzene system, can be considered as an benzene system can be considered as an benzene system can be considered uh, as a nucleophilic system because it is rich in electron and it can now welcome an attacking electrophile. But the thing is, it do not undergo addition reaction just like your alkene or alkyne or alkadine. Rather, it undergoes aromatic electrophilic substitution. Now, the basic question is, why does it undergoes aromatic electrophilic substitution? The answer to this question lies in the maintenance of aromaticity in the product. If benzene undergoes addition reaction, then it will loses its aromaticity. On the contrary, if it undergoes substitution reaction, its aromaticity will be retained. And that is why it undergoes aromatic electrophilic substitution reaction. Now, how does this aromatic electrophilic substitution takes place? The hydrogen on the one of the hydrogen on the benzene ring will be replaced by some electrophile and removing a proton from the benzene ring. This is one common kind of reaction. You need an attacking electrophile for this particular reaction. In addition to these, benzene do undergo aromatic nucleophilic substitution under special cases wherein you have some living nucleophile attached to the benzene ring and the nucleophile comes in and it replaces the attacking living nucleophile. However, this reaction is not very common in case of benzene. As far as your syllabus is concerned, we have to focus our attention on aromatic electrophilic substitution reaction only. Now moving forward, let us understand what is electrophilic substitution reaction. Now, before understanding it, as I mentioned earlier, that even though benzene has got 3 pi bond, it do not show addition reaction like your unsaturated hydrocarbon like alkene, alkyne and alkadine. Like if it undergoes this addition reaction, then you will notice that this 6 pi system for n plus 2 pi Huckel system will become anti-aromatic and will have only, it will not become anti-aromatic, it will become non-aromatic system because of the presence of 2 sp3 hybridized carbon atom, and it will lose its aromaticity during the addition reaction, and that is why addition reaction is not facile. One of the reason for this is loss of aromaticity in the product. On the contrary, if it undergoes a substitution reaction, say if this H plus is replaced by E plus, then in this case what will happen, you are retaining the aromaticity of the benzene ring. Now there are few very common reactions, aromatic electrophilic substitution reaction. These are halogenation, wherein you replace H by X. X could be chloro, bromo and iodo. Fluorination is a less common studied reaction because generation of a fluoronium ion, because fluoride can be easily generated, but fluoronium ion generation is bit difficult. Nitration, you replace H by NO2 group. Sulfonation, you replace H by SO3H group. Alkylation and acylation, you replace H by alkyl group and acyl group respectively. So these are the 5 different reactions which are very commonly studied in the context of aromatic electrophilic substitution reaction. We'll try to cover one by one, but before going for each reaction in detail, let us understand what is the product of these reactions in a nutshell. This single picture will tell you that benzene, this is the hydrogen which is being replaced by the attacking electrophile. The electrophile you will get from the chlorine. What is the source of electrophile? So in this particular chart, you need to focus your attention on what is the source of electrophile. Number one, what is the catalyst that you are going to use for the generation of the attacking electrophile. So looking at this, the source of electrophile is molecular chlorine or molecular bromine, and you have to use some Lewis acid catalyst. In all the cases, you have to use an acid catalyst for the generation of attacking electrophile. Say in case of chlorination, you use FeCl3. In case of nitration, you use sulfuric acid. In case of sulfonation, you use SO3 and H2SO4 as a catalyst. SO3 as a source and H2SO4 as a catalyst. In case of alkylation, you use a nitrous AlCl3 as a catalyst and alkyl halide as a source of electrophile. RCOCl means acyl chloride as a source of electrophile and anhydrous AlCl3 as a catalyst. And all these reactions, they have a common mechanism, and these are this common mechanism is initiated by the addition of electrophile to the aromatic system, forming a non-aromatic carbocation which is called as aranium ion, which is also known as valent intermediate or sigma complex intermediate. We'll try to cover these mechanisms one by one in more detail. Now let us understand how the general mechanism of aromatic electrophilic substitution takes place. So the first step will be the generation of an attacking electrophile. This attacking electrophile E plus is to be generated, and as I mentioned in the previous slide, you have to use a source of electrophile and you have to use a catalyst for the generation of this particular electrophile. So in case of halogenation, you use, say in case of chlorination, you will use chlorine plus FeCl3. So chlorine plus FeCl3 will give you chloronium ion and FeCl4, and that chloronium ion or say that electrophile will attack on the benzene ring, and there will be an electrophilic attack. As I mentioned, benzene is nucleophilic because of the presence of pi electron cloud. It will attack over the electrophile, and the addition of electrophile will generate an intermediate which is called as aranium ion or valent intermediate. This valent intermediate is very special in the sense that you got a positive charge and double bond in conjugation. So there is a possibility of resonance. So this is stabilized by resonance. Delocalization of the positive charge takes place by resonance, and you get this particular, these are the resonating structures of the valent intermediate or sigma complex intermediate, and this particular is a resonance hybrid of these intermediate, which will tell you that there will be a positive charge, partial positive charge at these particular 3 carbon atom. And in the last step, as it is a substitution reaction, one electrophile is to be replaced by another electrophile. So you have an attacking electrophile E plus, the leaving electrophile should be H plus. So in the last step, there will be a loss of proton. So this is a generalized mechanism of aromatic electrophilic substitution, wherein attacking electrophile comes in, gets the aranium intermediate, and in the last step, the proton loses, and you get your product. This will be the general mechanism. Now let us move forward and see the different reaction. This reaction is very, very important in the context of examination. So how to prepare the notes on this? I will give you some tips. First of all, you have to define what is nitration. So what is nitration? Nitration is essentially the replacement of hydrogen atom of the benzene nucleus by nitro group. This reaction is called as nitration. Benzene on treatment with nitrating mixture. As I mentioned, you need a source of electrophile and you need a catalyst. So what is the source of electrophile here? The source of electrophile is HNO3. And what is the catalyst here? Concentrated H2SO4. So what will happen? If you get NO2 out of it, what will be left? OH will be left. That OH and H will combine to give water, and you will get a nitrobenzene as a product. NO2 will go to the benzene ring and will replace H plus. So you will get the nitrobenzene as a product. Now let us have a look at the mechanism. The mechanism is very similar to the general mechanism of aromatic electrophilic substitution. Herein there are 3 important steps. These steps are very common. Formation of attacking electrophile, which may change from case to case. Like in case of nitration, it is a nitronium ion. Have a look at the word nitronium ion. What is nitronium ion? Nitronium ion is essentially here you have to look at the suffix IUM. IUM is a suffix which is usually being added to a positively charged species. How is this nitronium ion generated? We'll see in a little later, but there will be 3 steps. First one will be the formation of attacking electrophile, second will be the formation of sigma complex intermediate, and third will be the formation of a product which is eventually formed by the loss of proton in the last step. So let us have a look at these steps one by one. How the nitronium ion is formed. So you know that sulfuric acid is stronger than nitric acid. Even though nitric acid will ionize as H plus and NO3 minus, it will, in presence of H2SO4, it will ionize in a different manner. So what will happen? The sulfuric acid being stronger than nitric acid, sulfuric acid will give its proton to the oxygen atom, one of the oxygen on the nitrogen, and it will result in the formation of this particular species. And this particular species eventually loses a water molecule to form a nitronium ion. So this is the intermediate, this is the attacking electrophile that will attack over the benzene ring. So for the sake of simplicity, I am just writing NO2 positive, but you should keep this particular picture in your mind that NO2 positive will be like this. So attack will be on the nitrogen, not on the oxygen. Now, this is your attacking electrophile and it will be attacked by the benzene ring, which is nucleophilic in nature. The pi bond will attack over the benzene ring. What will happen? This pi bond in particular will break in such a way that here you will get a negative charge, here you will get a positive charge, here you will get a negative charge. And there will be a formation of a bond between carbon and the nitrogen of the nitronium ion, resulting in the formation of the positive charge. And you know that this is a positive charge in conjugation with the 2 pi bond. So eventually this will undergo resonance stabilization by delocalization. So delocalization of the charge will result in the resonance stabilization. So you can clearly see that the positive charge jumps from this to this carbon and then to this carbon. So you will get a sigma complex intermediate and whose resonance hybrid can be represented like this, right? In the last step, while writing the mechanism, one has to be very clear that you have to preferably take one of the resonating structure, not the resonance hybrid. So if you start with one of the resonating structures, and you can it is interesting to note that in the first step you get a after losing up you get HSO4 minus, which is a conjugate base of H2SO4. What is a conjugate base? I have already explained. According to the Laurie-Bronsted theory, when when an acid loses a proton, whatever is left will be a conjugate base. So this is what? This is a conjugate base of H2SO4. So what will happen? This conjugate base will take away the proton from the sigma complex intermediate and regenerating the aromaticity of the benzene ring. Mind here that negatively charged HSO4 minus is taking the proton. So this carbon hydrogen bond is broken in such a way that hydrogen goes from this sigma complex intermediate without any electrons. So electrons are left on the benzene ring. So here there will be a negative charge. So this negative and positive will generate a double bond, regenerating the aromaticity of the benzene ring. This is a generalized mechanism of the benzene ring. If you understand the mechanism of nitration, rest of the mechanisms are quite similar. Now let us move to the next reaction. Next reaction is Friedal Craft alkylation. Alkylation means you are replacing the hydrogen atom of the benzene ring by an alkyl group. Let us say if you want to get what will be the source of R plus? Source of R plus is the alkyl halide. So if you want to do the methylation, then you can do methyl chloride. So when you and what is the catalyst required? You require a Lewis acid here. In case of nitration, you use a Bronsted acid. Here you require a Lewis acid. So this Lewis acid are the acids which are electron deficient. They have affinity for the electron rich site. So they can take up, say, AlCl3 can combine with CH3Cl and can take away the Cl minus out of it. If a Cl minus is taken away, what will be left? CH3 positive. Okay. So how this reaction will take place? The reaction will take place this way. So your H will be replaced by CH3. Have a look at the color. I have leaving electrophile is mentioned in a red, attacking electrophile or the source of electrophile is shown in blue, and catalyst is shown in black in all the slides. Okay, so you will get methyl benzene or toluene as a product. Methyl benzene or toluene as a product. It is interesting to note that not only this anhydrous AlCl3, you can use different sorts of Lewis acid like FeCl3, SnCl4 can also be used. Other Lewis acids also works well in this particular reaction. Now looking at the mechanism, which is very similar to the nitration mechanism. Here the attacking electrophile is a methyl carbocation or alkyl carbocation in general. So methyl carbocation can be generated by treatment of this source of electrophile is methyl chloride. You can take any alkyl halide and you can do treat it with AlCl3 and you can get CH3 positive and AlCl4 minus. As I mentioned, this aluminium will take away this Cl minus and it will be converted into AlCl4 minus. This will be a species that will be utilized in the last step here. I'll talk a little later about that. Now this is your attacking electrophile which is generated in the step 1. Now it will attack on the benzene ring. So benzene ring will exert a nucleophilic attack resulting in the formation of a sigma complex intermediate. This is I forgot to tell you that this is a slow and a rate determining step. In organic chemistry, any step which is slow is called as rate determining step because you can determine the rate of the reaction from the slow step only. And I have shown it by a reversible arrow. So make sure that you are mentioning that it is a slow and rate determining step and make sure that you are using a reversible arrow. I already talked about the use of arrow in my earlier lectures, during my earlier live lectures to your class. So use arrow very sensibly. Reversible arrow is used, and here you can see the arrow of resonance, which is the double-headed arrow on both sides, which is used to show the resonating structures. So you will get a resonance stabilized sigma complex intermediate and his resonance hybrid can be shown like this. And in the last step, what is left? The first step, attacking electrophile is formed. In the second step, sigma complex intermediate is formed. Now in the third step, which should go? The living electrophile should leave the intermediate. So here the living electrophile is being taken away by AlCl4 minus, and this is the fast step resulting in the formation of a toluene, and AlCl4 will regenerate AlCl3 back and HCl will be taken away. So overall reaction, you will notice that CH3Cl plus benzene ring will give you toluene plus HCl will be formed as a byproduct in this particular reaction. Moving forward to one more reaction which is called as acylation reaction, and this acylation reaction involves the replacement of hydrogen atom by an acyl group. Acyl group is a COR group. Make sure that this C double bond COR is like C, then you have a double bond O, and then you have an R group here. It's not an ethereal linkage, it's a kind of a ketonic linkage. So what can be a source of acyl group then? The source of acyl group can be an acetyl chloride or it can be acetic anhydride. So acid derivative where you have the some living part, you can use it as an acyl group, source of an acyl group. So benzene on treatment with acetyl chloride. Acyl is a general name. Acetyl stands for, you know the nomenclature of acid chloride. Acid chlorides are named on the basis of their parent acid. This can be prepared, say CH3COOH. If you replace OH by Cl, you will get acid chloride. And how they are named? You have to replace IC acid by YL chloride, isn't it? So this is a YL. If I remove this and I replace it by IC acid, it becomes acetic acid. Okay, so when you treat benzene with acetyl chloride or acetic anhydride with in presence of a Lewis acid like anhydrous AlCl3 or FeCl3 or SnCl4, you can get acetophenone, you get a ketone. This is the versatility of this aromatic electrophilic substitution, that you can get varieties of the functional groups from the starting from the benzene. So this is very similar to the Friedal Craft alkylation reaction. Now moving forward to the mechanism, it is very similar to that of the Friedal Craft acylation. So here you need acyl carbocation. Acyl carbocation can be prepared by treatment of acyl chloride with AlCl3. This Cl minus will be taken away by Al and you will get AlCl4 minus and you will get COCH3, which is the acyl carbocation. This will attack on the benzene ring resulting in the formation of a sigma complex intermediate. I will not spare my time in explaining how the sigma complex intermediate is formed because we have already considered in the previous mechanism. You will get a resonance hybrid, and in the step 3 eventually AlCl4 minus will take away the proton, regenerating the aromaticity of the benzene ring to form the toluene. Sorry, there is a typos here, it's not toluene, It's acetophenone. What is it? It is acetophenone. Okay, acetophenone, or you can call acetylbenzene. So this compound is acetophenone. It is a bit difficult for me to type it on here, but I will try my level best. So it is acetophenone. Okay, it's not toluene. So make sure that this is a typos from my side. Apologies for that. So this is about the Friedal Craft acylation. Now moving forward, one more reaction that we will cover in today's video lecture will be the halogenation of benzene. Now benzene and its derivative undergo two types of halogenation. One is called nuclear halogenation, other is called side chain halogenation. The side chain halogenation is all about the, if you have an alkyl side chain on the benzene ring, say you have CH3 group here, then the halogenation can take place on the side chain or on the nucleus of the benzene ring. And when it takes place on the benzene, it is called as nuclear halogenation. So replacement of hydrogen of the benzene nucleus by halide, by halogen, you can say, not halide. So it is called as nuclear halogenation. So benzene on treatment with chlorine, molecular chlorine in presence of anhydrous FeCl3, which is a Lewis acid, gives chlorobenzene. You can use AlCl3 or SnCl4, which are the other Lewis acid, can also be used, but most commonly used, there is again a typos here, it should be FeCl3, not AlCl3. Yeah? So it should be FeCl3, not AlCl3. Yeah? So usually FeCl3 is a very commonly used because FeCl3 is a reasonably um, 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 less expensive reagent than AlCl3. Now again the mechanism would be simple. What will be the attacking electrophile? Attacking electrophile will be chloronium ion. Chloronium ion will be generated by the reaction of chlorine gas with FeCl3. You will get, this is your attacking electrophile, and you will get this is a conjugate base. Now this, similarly there will be an attack of the nucleophilic attack of the benzene ring on the chloronium ion, resulting in the formation of a sigma complex intermediate, which is very similar to the one which we have seen earlier. And in this last step, FeCl3 takes away the proton, regenerating the aromaticity of the benzene ring and formation of the chlorobenzene. Okay, so in a nutshell, what you need to focus? You need to focus on few important aspects. Number one, what is attacking electrophile? So identify the attacking electrophile. Say if it is a bromination, what is the attacking electrophile? If it's a bromination, attacking electrophile is Br positive. If it's chlorination, attacking electrophile is chlorine Cl positive. If it's nitration, attacking electrophile is NO2 positive. If it's sulfonation, the attacking electrophile is SO3H positive or SO3. If it's Friedal Craft alkylation, attacking electrophile is R+. If it's acylation, the attacking electrophile is RCO positive. Right? Now, these are essentially, these are the electrophiles, and how they can be generated? They can be generated by using a source of electrophile plus catalyst. What is the source of electrophile? If you want to do bromination, molecular bromine will be your catalyst, and you can use these sorts of catalyst. Catalyst are any Lewis acid like FeCl3, FeBr3, or in some cases iron powder is also used. In case of nitration, source of nitronium ion is HNO3 and the catalyst is H2SO4. In case of H2SO4 sulfonation, the oleum is a source of, so oleum means SO3, which is a liquid which is called oleum. So oleum or concentrated H2SO4 or fuming sulfuric acid. There is one more term which is commonly used called fuming sulfuric acid. Fuming sulfuric acid is a sulfuric acid which is having more amount of oleum in it, means more amount of SO3 in it, and which will be coming out in the form of fumes. If you open up the bottle, you will see the fumes of SO3 coming out of the bottle. In case of Friedal Craft alkylation, you use alkyl halide as a source and you use the Lewis acid, which is usually anhydrous AlCl3. Why anhydrous? Because if you use water containing salt, then it will spoil the reaction. Similarly, Friedal Craft acylation, you use acyl chloride or acid anhydride as a source of electrophile, acylium ion, and Lewis acid, which is usually AlCl3. Now, one more important aspect about the reaction is nitration. About the nitration is, here H2SO4 plays dual role. H2SO4 acts as a dehydrating agent because in the reaction you have noticed that water is formed as a byproduct. So H2SO4 is having affinity for water. So in the nitration, particularly in nitration, H2SO4 plays a dual role. It helps in the generation of a nitronium ion, number one, and number two, it takes away the water which is formed as a byproduct in the reaction. Recall the nitration reaction where in addition to the nitrobenzene, you get water as a byproduct. That water is to be taken away by some dehydrating agent, otherwise the equilibrium will shift in the backward direction. So in order to, so H2SO4, it plays two roles. Number one, it helps in the generation of attacking electrophile nitronium ion, and number two, it takes away the water which is formed as a byproduct in the last step. So this is all about the aromatic electrophilic substitution reaction.